what is the actual fundamental difference between an element and a nuclide? I mean, we throw these words around all the time in science class, but pinning down the exact distinction, that is absolutely crucial to understanding how our physical universe is stitched together at the most microscopic level.
Welcome to today's Explainer. I am genuinely super excited to guide you through this today. We're going to take a really structured, fascinating look into the underlying rules of the universe. We'll break down the terminology, unpack the math behind the nucleus of an atom, clear up some really common misconceptions, and hopefully give you a rock-solid foundation on what makes atoms actually tick.
All right, let's dive into this. Here is our roadmap. We're starting with defining the nuclide, then we'll meet the isotopes, explore why they're chemical twins but nuclear strangers, look at measuring isotopic abundance, and finally, we'll wrap the whole thing up with a pop quiz on the nitrogen nucleus. Section 1. Defining the nuclide, the foundation of the nucleus.
Okay, to really grasp atoms, we've got to define this term, the nuclide. Officially, a nuclide is defined as a, quote, species of a nucleus. But what does that actually mean for us? Well, it means a nucleus that has a very specific Z and a specific A. Z is the atomic number. That's the exact number of protons. Think of Z as the master switch. It dictates the entire identity of the element because those protons pull in the electrons that ultimately drive literally all chemical reactions. If Z is 1, boom, it's hydrogen. If Z is 6, it's carbon. Then we have A, the mass number. This is the heavy stuff, the total number of protons plus neutrons packed together in there. You absolutely need both of these specific numbers, Z and A, to definitively identify any single nuclide.
And you know, we aren't just making these letters up for fun. These strict scientific conventions for atomic and mass numbers, they form the rigorous, universal language of physics and chemistry. Everyone all over the world has to be on the exact same page.
So this brings us to an absolutely inflexible rule. If you change either the Z, the protons, or the A, the total mass, you no longer have the same nuclide. You just don't. You have an entirely different nuclide. And because the nucleus has been fundamentally changed on a structural level, it's going to have entirely different nuclear properties. Keep this rule tucked in your back pocket because it is the master key to this whole puzzle.
Section 2. Meet the isotopes, same Z, different A.
It helps to think of an element kind of like a family. By definition, all hydrogen atoms have a Z of 1. They all have exactly 1 proton, no exceptions. But let's look at their mass, their A. Normal, everyday hydrogen has a mass of 1. But deuterium, its slightly heavier sibling, has a mass of 2, meaning it has 1 proton and 1 neutron. Then there's tritium with a mass of 3, 1 proton, 2 neutrons. Because they share the exact same Z, but have a totally different A, we call them isotopes. They are all hydrogen, just functioning at completely different weight classes.
And this doesn't just happen with the tiny lightweight stuff. It happens way down at the extreme heavy end of the periodic table too. Massive elements like uranium come in a bunch of different naturally occurring isotopic flavors. Uranium-233, uranium-235, uranium-238. They are all definitively uranium because that proton count is perfectly identical, but their total mass varies drastically because of those extra, super heavy neutrons.
Now here is where we have to be incredibly careful with our terminology. The source material actually features this brilliant little sidebar warning about a conceptual trap that catches a lot of people. You'll often hear someone say, quote, uranium-235 and thorium-232 are different isotopes, and according to our rigorous scientific definitions, that statement is just completely wrong.
Let's break down exactly why that's wrong. Uranium-235 is an isotope of uranium. Thorium-232 is an isotope of thorium. Uranium and thorium are entirely different elements. They have entirely different Z numbers, which means a completely different amount of protons, so they can't be isotopes of each other. As the text lays out, it's so much more accurate to just say they are completely different nuclides. Remember, every single individual isotope of an element is its own distinct nuclide.
Section 3. Chemical twins, nuclear strangers. I absolutely love this concept because isotopes of an element have the exact same number of protons and therefore pull in the exact same number of electrons to orbit them. They are basically chemical twins. In a chemistry lab sitting in a beaker, they're going to react identically. Your own body processes carbon-12 exactly the same way it processes carbon-14, but inside the nucleus, they are total strangers. Isotopes can have wildly different nuclear properties. One might be perfectly stable for all of eternity, while its chemical twin might be highly radioactive and literally split apart in a matter of seconds. Basically, chemistry only cares about the protons and electrons. Physics cares about the whole nuclide.
All right, Section 4, measuring isotopic abundance.
Zooming out to the real world for a second, elements don't usually just exist as one single pure nuclide. Most naturally occurring elements are a mix of two or more isotopes. Our source defines abundance as the fractional presence of an isotope in a naturally occurring quantity of that atom. It's kind of like nature's fixed recipe. If you go outside and scoop up a handful of naturally occurring carbon, it will always be a mix of different isotopes existing in very definite, fixed mathematical proportions. And hey, there's a really vital, easily missed detail in the text here. When scientists give us these isotopic abundance percentages, they're generally providing them only for the stable isotopes of an element. Why? Because the radioactive ones are constantly decaying and changing into other things, so they just don't have a fixed, stable natural abundance that we can easily list out in the same fractional way.
Section 5. Pop quiz, the nitrogen nucleus. Let's see if we've been paying attention.
We've covered a lot of ground, so let's apply it. Here is a short answer question directly from our text to test our focus. We start with nitrogen 15. The symbol shows 15 on top for the total mass and 7 on the bottom for the protons. That means it has 7 protons, and well, 15 minus 7 is 8, so it has 8 neutrons. The question asks, if a single proton is removed from this nucleus, does it become nitrogen 14? Is this statement right or wrong? Let's figure this out together.
Let's just methodically walk through the math step by step. Step 1, we start with Z equals 7 and 8 neutrons. Step 2, we remove 1 proton. Okay, so now our new Z is 6. The neutrons haven't changed at all, they're still at 8. Step 3, what is our new total mass, our new A? Well, 6 protons plus 8 neutrons equals 14, so the top number is indeed 14. But wait, look at step 4. The Z number, that fundamental master switch of the element's identity, it changed to 6. And if you go check a periodic table right now, atomic number 6 is definitely not nitrogen. Atomic number 6 is carbon.
So the statement in the book is fundamentally wrong. It's a trick question. By changing the number of protons, you don't just magically create an isotope of nitrogen. You completely change the element. It doesn't become nitrogen 14, it becomes carbon 14. Remember the golden rule. The Z number absolutely always dictates the true elemental identity. Which really brings us to a fascinating final thought to wrap up this explainer. We just proved mathematically that changing the contents of a nucleus literally transforms one element into another. So, look down at your own hand for a second. Considering that the carbon, the nitrogen, the hydrogen making up your very cells are all specific stable isotopes existing in these exact natural abundances, what massive, cosmic, atom-smashing forces were required out there in the universe to originally build those exact nuclides billions of years ago? It's definitely something to chew on. Until next time, keep exploring and keep asking questions.